So thank you very much for giving me the opportunity to speak here. So I will talk about finite-N indices from branes and negative branes. So this is based on this paper and on work in progress with Gayotto. Okay, so ADS-CFT has been studied extensively in the large N limit. So the large N expansion corresponds to the perturbative string theory expansion. So these are loops in target space. And then finite-N effects on both sides are non-perturbative effects. So for example, on the gauge theory side, we have trace relations. Okay, so because the sizes of the matrices are now finite, certain multi-trace operators satisfy relations. So for example, for a matrix in SU2, the following is true. So at infinite N, this would be two different operators, and at finite N, they are related. So this is what I mean by trace relations. Now, on the string theory side, the non-perturbative effects are d-branes. So at finite N, d-branes become dynamical. They have excitations, open strings. So for example, to compute finite N Hilbert space, we would expect we should include contributions from both closed strings and branes. So natural setting to study these finite N effects are supersymmetric indices. So supersymmetric indices count protected operators with signs, and they don't depend on couplings. And recently, in the last few years, there's been some progress in computing the finite N indices. So we have these, what's known as giant graviton expansions. So these are formulas that look like this. So we have a finite N index, and we have an infinite index, and we have an infinite sum of corrections. Okay, so for example, we can take this to be the superconformal index of N equals 4 super Yang-Mills. And then this has a nice holographic interpretation. So then you can think about this Z infinity as counting multigravitons. So closed strings. And then these corrections are now related to branes. So in particular, for N equals 4 super Yang-Mills, these are giant graviton branes, which are the free branes that drop a line in ADS and S3 inside S5. Okay. So we have the finite N index, we have the infinite N index, which you can think about as counting multigravitons, and we have the corrections, which are related to the branes. Okay, so this picture motivates us to try to combine the closed strings and branes, and then mod by some type of redundancy to arrive at the finite N index. Okay, so there's multiple expansions. And so today I will focus on the expansion by Murphy. And one of the results I will explain is that the corrections in Murphy can be understood as k/k d5 branes. So this is a stack of branes and negative branes, such that the gauge group is now UK/k. And then these branes, they parameterize the moduli space of this giant graviton d3 branes. Okay, so the plan is that first I will review U and indices, and then we will generalize to UN/M in order to be able to talk about these branes. And then we will try to apply this to Murphy's giant graviton expansion. And then I will give like a tentative construction for a Finite-N Hilbert space, which categorifies discounting. Okay, so I will start by reviewing UN indices. So let's assume that we have a UN matrix, and we want to count all the operators which are invariant under adjoint transformations. So these gauge invariant operators, they are generated by traces. So for example, we have trace x squared, trace x to the n. Can I still write here? Okay. And we also have multi-traces. So it's products of this, right? And we stop at n because trace x n plus 1 turns out that we can rewrite it using products of shorter traces. Okay, so this is the Cayley-Hamilton formula. And this is, again, an example of a trace relation, that for operators that are longer than n, we can rewrite them using shorter operators. Okay, so it's convenient to package this into a generating function. So we want the generating function. We introduce some fugacity little x. Such that these coefficients, they tell us how many linearly independent operators of length n we have. So in this simple case, we can compute this just by hand. So Zn is okay, is this clear? So for example, 1 over 1 minus x, it counts polynomials in trace x. And the next factor counts polynomials in trace x squared. And then we have a product because we can multiply them. And we stop at n because of this trace relation. Okay, so in this simple case of one matrix, we can just compute this generating function by hand. Now, for more than one matrix, we no longer have such closed form formulas. So where is? So for example, recently there's been a lot of work by Rob de Mello-Koch and collaborators on, in particular, computing these generating functions for more matrices, but there usually aren't closed formulas for any n. So one way to compute these generating functions is the Moyen-Weil formula. It's an integral formula. let me explain the ingredients here. Yeah? Oh, sorry. So little f is a single letter index. Either, right? So it's a single letter partition function or index, depends on what you want to compute. So this counts what are the letters from which we are building the gauge invariant words. So for example, if we have just one matrix, then little f would be just little x. If we had two matrices, it would be x plus y. And if we were computing an index and we had a fermion, then for example, we could have this. The PE is a plethystic exponent. So this computes the index of all the polynomials in letters we can make out of these letters. So for example, PE of a bosonic letter, 1 over 1 minus x. Because we either don't put the letter, we put one letter, or we put two letters, etc. And P of a fermionic letter is just 1 minus x, because we either don't put the letter or we put one letter. Okay, so F counts all the letters, PE counts all the words and polynomials in words, and then these U are gauge fugacities, so they keep track of how the letters transform under adjoint transformation. This is the van der Monde determinant. And the point of this integral is that it projects on the gauge invariant words. Okay, so this works for like any counting problem when you have some matrices and you want to count the gauge invariant words. In particular, it also works for supersymmetric indices. Since supersymmetric indices don't depend on coupling, we can compute them in the free limit, and in the free limit you again have some counting problem. Okay, so we will be interested in quantities like this. So the difference between the finite-N and the infinite-N index. And the giant graviton expansion by Murphy gives sort of an infinite sum of corrections for this. And it turns out that these corrections, they are actually related to UK/K indices. Okay, so now we are going to generalize this formula to UK/K.
Sorry, just a small thing. Earlier you wrote a formula where Z infinity was a product.
Yeah, you're right, sorry.
Okay.
And now from 1, yeah, thank you. Okay, so now we are going to discuss UN/M invariance. Okay, so we have a UN/M matrix. So it looks like this. So A and D are bosonic blocks, and B and C are fermionic blocks. And you can get this sort of gauge group in string theory when you consider branes and negative branes. Okay, so this would be branes with a Chan-Paton bundle, Cn/M. So then the open strings, they are Un/M matrices. Okay, so now the gauge invariant operators, they are generated by supertraces. Okay, so a trace would be with a plus. So that's no longer the gauge invariant thing. The gauge invariant operators are supertraces. Okay, so now we would like to count polynomials.
Yeah. If you take the usual trace instead of supertrace, do you still what's wrong with that?
It's just not a gauge invariant thing anymore. Yeah.
But still gauge invariant for the SU
version, or it's just it's not gauge invariant?
No, I think it's not.
Oh,
So the yeah, it's supertraces.
okay.
Okay. So we would like to count all the polynomials in supertraces. So we are going. So now we would like to generalize this formula. Okay. So let's write like a naive generalization. Is this big enough, or? Yeah. Okay. So now we are integrating over two sets of variables, u, which are the first n eigenvalues, and v, which are the second m eigenvalues. We have a super Vandermonde. And we change the character of the adjoint representation to the character of the adjoint representation of Un/M here. Okay, so now we have the following problem that, so I didn't write it, but, oh, I did. So we were integrating over the unit contour. So now this Vandermonde has poles here. So we have to somehow deform the contour. So for example, we can do this. Okay. So this is like a naive generalization of the Mullian-Weil formula to Un/M.
Is there some ambiguity in how you deform the contour? Right, like in this Imamura style expansion, you'll get different answers depending on exactly which contour you take. And
Yeah, so I just have one proposal
yeah.
where the contour is this, but there's probably, you could try to change it, yeah. So I will now say, like, so what the proposal is. So the claim is that this doesn't compute the invariance, but a sum of these integrals computes the invariance. Okay, so if this is a generating function of un plus k slash k invariance, then the conjecture is that it's given by a sum of these integrals. Okay, so this is big K, this is little k. So when little k is equal to 0, then this just reduces to the normal un Mullian-Weil formula. And then we have these corrections. So you can think about this as coming from these inclusions. Right, so un plus 1 slash 1, they have different trace relations. And these z plus integrals, they somehow correctly add them. Yeah?
But on the right hand side, when you write graviton index, that was like index on a giant gravitons.
Yeah, so we're not doing the giant graviton expansion yet. I'm just trying to explain how to compute invariance of un slash m.
Yeah,
So
but
this
like
is not a
naively, I'm
giant-
saying, why is it not uk, but it's uk slash k? You're going to explain that?
So we are not doing this yet.
Okay.
I'm just explaining in general, if you wanted to compute generating function of like u2 slash 1, then you should use this formula, like that it's a sum of things. And we are going to do this later. But for example, if you want zk slash k, then it's a sum, starts with 1, and then you have this 1 slash 1 plus, blah, blah, blah.
So the left-hand side of that formula, do you also have a plus on the z?
No, so the left-hand side is just generating function of un plus k slash k invariance. And I'm saying it's computed by the sum. Yeah, so it's different than un, right? In un, you just have one integral. Here you have a sum of these integrals. And now it would be very interesting if one could find like a nicer formula that's just like one integral that somehow reduces to this. Maybe by considering different contours or something like that, but I was not able to find it.
So is that experimental, or do you have some other motivation for this sum?
I mean, no, this is experimental, but so I will do an example for one matrix where it agrees with like known mathematical results. And there also was like a preprint with a proof recently.
So if there is a proof, why do you call it a conjecture?
Sorry, so because I don't know, like in math, I think you're supposed to wait for it to be published. Yeah, so it just was recent, so I don't know. Like for example, I cannot follow the proof phrase. Okay, but so now let's consider this in k goes to infinity limit. Okay, so it's something like this.
You gotta write capital and lowercase k differently.
So this is big K. I'm sorry. Yeah. Okay, so first of all, let me convince you that this should be true for any n. So this counts super traces. This counts traces. So these are different objects. But here, the size of the matrix is infinite. So there's no supertrace relations. And here, the size of the matrix is infinite. So there's also no trace relations. So like for any supertrace, I can just write a trace. And these are different objects, but because there's no trace relations on either side, then they are just one-to-one, like symbolically. Okay? Okay, but now we just said that the left-hand side, you should actually compute it by the sum, right? Okay, so the second conjecture is that there is like a negative brane expansion. It looks like this. Okay, so this is the infinity, and then this is the n plus infinity slash infinity, which is computed by the sum. Okay, so here we have the finite-N index, here we have infinite index, and here we have a bunch of corrections. Okay, so this is not really a giant graviton expansion, so this is different from the strand graviton expansions that I listed. So you should think about this as just coming from these inclusions. Okay, so this is like a different way to resolve trace relations. So this has different trace relations than this. So you keep adding the trace relations until there's no trace relations left, and you have the infinity. Okay, I will leave this. Okay, so now let's do a one matrix example. Okay, so just like at the beginning, we take little f equals to little x, and we just consider one un slash m matrix. So for this simple case, we can do these integrals, and this is the result. This is the Pokamer. Okay, so in particular, you can see that this starts from x n plus 1. It starts from this power. It doesn't start from 1, right? So this integral cannot compute the full index because we would like to start from 1. Okay, so then the full index is given by a sum of this. And so for one matrix, this problem of counting super invariants is actually equivalent to like this known problem of counting supersymmetric polynomials. So if we diagonalize this one matrix, then super traces of powers of x, they are just given by these power sums. So this would be the first eigenvalues and then the other eigenvalues. And so polynomials that are generated by such power sums, they are called supersymmetric polynomials. So there are known formulas for the generating functions of these supersymmetric polynomials, and they match this. Okay. And now we can consider this expansion for one matrix. So this expansion for one matrix, it turns out it reduces to some known combinatorial identities. So this is for n equals to 0, and this is for any n. These are some known combinatorial identities by Cauchy and Euler. And now for more matrices, so there's no longer known formulas for this to compare, but one can check just like by listing all the operators in Mathematica. And there's also this proposed proof recently.
And just one matrix example, if you choose different contours, can you get different kind of prefactors for C pluses, or is that in a case where you can kind of do all the integrals explicitly, right? So then it should be sensitive to the contour choice.
Yeah, that's a good idea, but I didn't do it. Yeah.
I think this was maybe done by Jim Liu in the case of like Imamura style expansion, or was it Jim Liu? You guys did something like that, right? Where you showed the different contour choices.
It's not as subtle. We're looking at Murphy's expansion and sorry, it's a little bit subtle. I think in this sort of example of Murphy's thing, we did not necessarily change any contours, but in Mamura's case, we were demonstrating different types of analytic continuation versus, pole selection and things like that. It's a complicated issue. I don't know. We should think about that.
Yeah, well, I tried changing the contours in such a way that it all collapses to one thing, but that never happened. But I guess you could maybe arrive at different identities like this with different choices. I didn't think of it, yeah. Okay. So we reviewed how to do UN and UN/M invariants. So now we are going to come back to the giant graviton expansion by Murphy. Okay, so now we have finite-N here, infinite-N here, and infinitely many corrections. So like we said, these corrections have to somehow implement trace relations. And then these corrections, you can sort of think about them as they come with like overall signs, like minus, plus, minus, plus. So of course, if you have some fermions, then there's going to be minuses anyway, but there's like an overall minus. So you subtract trace relations, but then you subtract too much, and then the next correction adds, but it adds too much, and it goes on. Okay, and this also works for any counting problem. So this was proven by Murphy for any sort of generating function that's given by, that's of the form of this Mollian-Weil integral that we wrote at the beginning. But we are going to focus on the example of n equals 4 super-young meals. And also, so this is different than this expansion that I wrote before. So if we just shift it to the other side, it's going to be, in general, different. OK, so now let's write these corrections. So, OK, I want to keep this. So So in the original paper by Murphy, these corrections were given in a different form. And then there were these subsequent papers where they more or less arrived to this form of these corrections. And in particular, it was noticed by Dan that this looks like a UK/K matrix integral. And we can take the same contour here. So this was the motivation to study just like indices of UN/M. Right, so there are basically two differences with these G's and these ZKs. There is this, and there's this. So first of all, let's focus on this. So this looks like a UK/K integral, but with a different effective index, right? So this little f here was counting what are all the letters from which we are making the gauge invariant the gauge invariant operators. So it looks like this is a UK/K integral, but with different single letter index. Define this. So now I'm going to explain that this is actually the index of the branes that are completely transverse to the original branes. Okay, so let's focus on the n=4 example. So let's say that the little f is the index of ND3 branes. And so because we are looking at supersymmetric indices, it's convenient to just think about branes in topological strings. So we can just consider ND3 branes in C5. Because the supersymmetric indices, they only see the BPS excitations they count. They correspond to excitations of just branes in topological strings. Okay, and then, so it turns out that this f shrik, this is actually the index of the branes that would be completely transverse. So it would be D5s. because 4 plus 6 is 10. And it looks like we get k/k d5s. Okay. So we can check this. So if you are familiar with the index of n equals 4 superennials, it looks like this. And there's 5 fugacities with 1 condition. Okay, but if not, then you should just trust me that it always works like this, that the numerator, it tells you how many transverse directions you have to the brane. So in this case, we have 3 transverse complex directions. And the denominator, it tells you how many parallel complex directions we have, because the denominator counts derivatives. So we have 3 complex transverse and 2 complex parallel, so it's a D3 brane in C5. Okay, so now let's compute this F shriek. So what this F shriek does, it just flips this numerator and denominator. So now we have 2 complex transverse directions and 3 complex parallel directions. So we end up with a D5 brane in C5. And you can see that the transverse and parallel directions got flipped. So it's the D5 that's completely transverse. Okay.
One real quick question. You made this quick remark that the denominator should be thought of as counting derivatives. I wasn't really following that logic. How do I think of that?
Yeah, so let's say I have some, so the 116 BPS subsector has 2 derivatives. It has like 3 scalars, 3 fermions, and an F. So if I have 2 derivatives, then I can have a scalar without a derivative, or with 1 derivative, or with 2 derivatives. Right, so this exponentiates to these denominators. So these are actually 2 holomorphic derivatives. That's why you have 2 complex transverse directions. Okay, so the first observation is that in Murphy's giant graviton expansions, these corrections are related to the completely transverse branes. Okay, so the second, okay, now let's set n equals to 0 to get rid of this. Sorry. So now we see that these GKs for n equals to 0, they are equivalent to this Z plus, but for a different F, right? For F shriek. And then there's one more observation. So the infinity of F and the infinity of F shriek actually multiply to 1. So one can check that. So now let's write this negative brane expansion for F shriek. Okay, and let's divide by this, which is the same as multiplying by this. because these z plus are the same as these gk's for f. Okay, and 1 is actually just z of n equals to 0. Okay, so for n equals to 0, these two expansions are equivalent. And this is easy to see because in this previous expansion, we were really just like, we had n branes, and then we were just adding one positive, one negative brane. In Morphy, we have n branes, and then we have transverse k/k branes. But if n is equal to 0, then in both cases, we just have a bunch of k/k branes. But we just look at them like this. So in this, for n equals to 0, these two are the same. Okay. So now what about this term? So the n bigger than 0, that's a bit more difficult. But one can show that this term actually comes from these extra bifundamental strings here. So it was also noticed by Dan that this term looks like an insertion of a superdeterminant, and it matches the term that would come from integrating out these bifundamental strings. Okay. Okay, and then the third observation about this Morphy's expansion is that we just learned that it's actually a sum of these GKs that should be interpreted as an index of k/k branes. Okay, so it's not a single GK that corresponds to k/k branes. It's a sum of these GKs. And then taking k to infinity, big K, it's like taking infinitely many branes and negative branes. Okay. So now we have an understanding of Morphy's giant graviton expansion at the level of indices. So this is the Finite-N index, which would correspond to these branes. Okay, I don't have more. This is an index of k/k, the 5 branes. But we take an infinite sum, so we take k to infinity. And also these bifundamental strings. And then we have z infinity here, which corresponds to closed strings. Okay, so it looks like to recover the Finite-N index, we should consider these k/k adjoint strings, these bifundamental strings, and closed strings. So when we take all of this, it obviously looks like there's too much, so one should try to mod by some kind of redundancy. So the work in progress with Gayoto is that we have a proposal for the Finite-N Hilbert space, which is built from these closed strings, these k by k adjoint strings, fundamentals. And when you consider this, there's a lot of overcounting. And we try to impose this overcounting by adding cohomologically, by adding an appropriate differential. So this should kill the redundancy cohomologically. Okay, so this is all I wanted to say, so let me just finish with some future directions.
Question. So, are the degeneracies that you get from the k/k adjoint and the bifundamentals, are they all additive in your case?
What added?
Are they all additive? Because in a non-super, just ordinary giant graviton expansion, the degeneracy is contributed by like the kth term. It comes with signs, right? The overall signs.
Yeah.
So there is naturally this this redundancy implementation via the degeneracies contributed by the branes. I'm wondering if that is the case, or you need to introduce extra structure to implement the some relations on top of what's there.
Yeah. So there's like two things. So one thing is that so there are the redundancies have redundancies. So that happens. So there are relations between redundancies.
Right. But isn't that already accounted for by the kth brane contribution?
Yeah. So it's a weird thing because it really, to me, it looks like sort of this sum, at least in this type of expansion, it really comes because you have k/k invariants. And as we've learned, if you want to do k/k invariants, you have to take sums. So it just looks like when you increase k to infinity, that's why you end up with this sum. So it looks a little bit different from like what you were doing to me.
So
this k is not associated with like redundancies of redundancies, I think. Maybe it secretly is, but
is the addition of q like a extra structure that one has to like have on top of this formula, or have on top of the degeneracies that you have from the adjoint and the bifundamentals, or is it?
No, not really. So
is it like an interpretation of the terms that you get
it's
from
basically
the
like the
adjoint?
natural like BV differential when you have some fermions and you have ghosts for these fermions.
Yes.
There's a differential, and it's just this differential.
Well, yeah, in like the non-super giant graviton expansions, the higher k terms, like they are the ghosts for the trace relations, right? So
yeah, so it's not exactly like k equals to 1 is the first redundancy, k equals to 2 is the redundancy of redundancy. It's not going to be like this here. Okay. Okay, so I just wanted to mention some possible future directions. So one could try to do holography for UN/N. So there are some papers that consider these holographic duals for UN/M. So the general idea was that like UN and UN plus k/k, these are equivalent in the n goes to infinity limit perturbatively. So these are perturbatively equivalent in n goes to infinity, but they will differ non-perturbatively. So, for example, we saw that these two gauge groups, these two theories will have different trace relations and different indices. So then presumably the holographic duals would have something like different branes or different black holes or different fortuitous operators. So So I didn't explain what are fortuitous operators, but so this will be explained later this week. But for example, one could consider cases like U2, U3/1, because these spheres have different trace relations. Whatever is fortuitous here due to the SU2 trace relation should not be fortuitous here, and things like this. One can also consider these integrals in the like large N and M limit. So this is so people have studied saddles of like UN integrals. So one could also try to study saddles of UN plus UN/M integrals. So it's work in progress with Matthew. And then going back to like standard holography, like UN holography. So it looks like these UK/K integrals, they appear when you go to Finite-N. And now, so this is like a standard construction in topological strings to consider K/K, like for example, space filling branes. And then the lower dimensional branes can be obtained by tachyon condensing from the higher dimensional branes. So this is sort of, this has a known meaning in topological strings. Now it would be nice to try to figure out like the holographic dictionary to actual physical strings. So, so I'm not exactly sure, for example, what is the picture for this in physical strings, if we are actually supposed to put these negative branes there, or maybe these branes are there but with some ghost number. So it would be nice to develop a better dictionary for these K/K branes in physical strings. Okay, thank you.
All right, so we open now for discussions.
So thanks for a very inspiring talk. The negative branes, as you said towards the very end, you were not sure if they should actually be taken seriously or whether there were some kind of ghost types or accounting device or something. But to me, it seems quite reasonable that you should have actual branes and anti-branes. But for that, you do not get a UN/M gauge group. You get instead a Quillen connection instead of a. So that's a super connection of a different type. Basically, instead of having your ABCD where B and C being fermions, you get where B and C are tachyons, because brane anti-branes have tachyons. And that object has a really beautiful index theory. It's just K-theory indices instead of standard Grassmann type indices, but it works very much the same. So might it be that these are really brane anti-branes, except the object is not exactly UN/M, but it's, which is a gauge, you have a gauge connection on UN/M, right? But Quillen's super connection is a K-theory connection, and it's, as I say, it has a super trace. The super trace works the exact same way. And it just seems like, okay, so that would be the natural object. And those are actually physical. This is what an actual DD bar system is described by.
So the reason I thought that these cannot be just anti-branes because brane anti-brane is not going to be BPS, right? And here we're talking about like BPS indices.
Yeah. So, but anyway, K-theory has been very good in classifying bundles of DD bars, and it has an index, and that index has a lot in common with the structure that you are having here.
Yeah. So the structure that you get for branes and anti-branes in physical strings turns out to be like very similar structure that you get for branes and negative branes in topological strings. So it's even to the point that people in topological strings, they actually say anti-branes, but they mean negative branes. And then there's also like a version of tachyon condensation, but those are not the same tachyons as like the branes and anti-branes. Those are like topological version of tachyons. So it just happens that like, yeah, the brane anti-brane picture is very similar for branes and negative branes in topological strings. And now maybe that is actually related to branes and anti-branes, but I thought not. Like.
Very good. Negative is not anti. Very good.
Yeah, yeah.
So, like, if you're computing this index from gravity, do these G, N come from some saddles which are like branes wrapping S5 or something?
Yeah, okay, so this is all like in flat space before back reaction, and we were just counting indices of these strings. So I don't know how to compute it in gravity. It looks like it would be a D5 that wraps S5, but I cannot be like completely sure.
Thank you.
In principle, these sums need to be explicitly computed all the way. Are there any approaches that one can take for actually perform these integers?
Yeah, so I didn't give any examples really, but it's always if you just compute this index to some order, like each term will only get like contribution from finitely many of these G's. So you can just, if you truncate it, I just need to look at like up to the like square root of k, I think. Yeah, so this is how in practice people do this. And I think computing these G's, even for one matrix, I don't think there's a closed formula for any k and n, but I'm not sure. Yeah, it's very hard to do these Mullian-Weil integrals like in general, not actually by residues.
That's something you can prove that for fixed n, you only need like finitely many k.
Yeah, you can. I'm guessing you could prove that. Like in those like z pluses that I computed, there, for example, it always started like here, right? That was the first term. So something like this always happens in these expansions.
All right, so if there are no further questions, let's thank Kasia again. So as I mentioned before, for lunch, you are on your own, but we will reconvene at 2 p.m. So if you don't know exactly whom to ask or where to go, we have graduate students that will be happy to guide you.